Okay, so in today's video we're going to be looking at maximum and minimum problems. Sometimes these are referred to as optimization problems. So essentially these are applications of stationary points really. So what we are looking for here is a problem where we need to either minimize or maximize a particular quantity. So we might be trying to minimize cost or surface area or whatever it might be, or we might be trying to maximize profit or volume or area or whatever. So the difficulty with these problems is not in the solving of them, it is in the construction and the formulation of the problem. So essentially I want you to think about them as a sort of four-step process. The first step is relatively straightforward, and that is to read the question and to work out what is the quantity that I'm trying to minimize or maximize. The second thing is to then and step two is the most difficult and time-consuming step quite often, and that is to find or construct an equation that describes the required quantity. So if we're trying to minimize cost, we're going to need an equation that describes cost, and that equation must be in terms of only one other variable so that we can then focus on maximizing or minimizing that quantity. The third step is then, once we've got our function to describe cost, we then want to find where is the minimum value of the cost function. So you want to find the absolute maximum or minimum of the minimum point of the equation found in step 2, including justification that that point gives a max or a min. So it's not enough just to find where the derivative is 0. That only tells you your function has a stationary point. You need to also verify that it is indeed a minimum point if you're trying to minimize the quantity. And then the final thing seems a rather trivial step, but is to answer the question. Does the question ask you for the minimum cost? Does it ask you for the value of x that gives minimum cost? Does it ask you for both those things? What accuracy does it ask for? Etc, etc, etc. Okay, so making sure that you've fully answered the question by the end. Okay, let's have a look at some examples. We'll work through a series of 5 examples here. So this could be quite a lengthy video, so you might want to watch a couple of examples, go and attempt some questions yourself, come back and watch the remaining examples, or whatever suits you. Okay, so the first example, a cylindrical tin canister closed at both ends has a surface area of 100 centimetres squared. And we want to find the greatest volume it can have. Okay, so we are trying to maximise volume. Step 1, done. So we're going to need, therefore, an equation about the volume of this tin canister. So let's have a think about what we've got here. So it's a cylindrical tin canister. So we have a cylinder closed at both ends. That's an important statement. That tells us about the fact that we do have lids on both ends, so it has a top and a bottom. Right, let's think about some dimensions. So a cylinder is defined by its height and its radius or diameter. We'll go with radius. It makes the formula construction easier. Okay, so volume is what we're trying to maximize, greatest volume. So the volume of a cylinder is area of the base times the height, so that is pi r squared times h. Now remember that when we find our equation to describe volume, it needs to be in terms of only one variable, and at the moment it is in terms of 2 variables, radius and height. So we need to now find a way to connect radius and height to each other so that we can express r in terms of h or h in terms of r, and therefore substitute into this equation and have volume in terms of only r or only h. And so the key bit of information that's going to allow us to do that is that we know that the surface area of this can is 100 centimetres squared. So surface area of a cylinder. Okay, you've got the 2 circles on either end. We're told it's closed at both ends, so that's 2 pi r squared being the area of a circle, and you've got 2 of those. And then we've got the curved surface. So when you unfurl a cylinder, that curved surface forms a rectangle. It's a rectangle with a height equivalent to the height of the cylinder, and the width or the length of the rectangle would be the circumference of the circle, which is 2 pi r. So the area of that rectangle would be 2 pi r times h. Okay, I'm pretty sure, I haven't got it to hand, but actually yes I do. The formula sheet for Maths Methods includes curved surface area of a cylinder. So it doesn't give you surface area of a cylinder, so it tells you though that the curved surface area is 2 pi rh, and then obviously you can use your own skills to add on the area of 2 circles, which is 2 pi r squared. Okay, so surface area is given by that. In this instance, we know that the surface area is 100. Okay, so then we think about, is it going to be easier to make R the subject here or H? Much easier to make H the subject. There's only one instance of H. So let's subtract 2 pi R squared. And then we can divide by 2 pi R. So H is going to be 100 minus 2 pi R squared over 2 pi R. It's a nice common factor of 2 there. Let's get rid of that and just keep our numbers a bit smaller. So pi R squared over pi R. And you could also break that fraction up if you want, but I'm going to leave it as it is. Okay, so now this is H. It goes into our equation for volume, so that we're now going to have volume just in terms of R. So volume is going to be pi R squared times H, which is 50 minus pi R squared over pi R. Okay, so we can simplify that. That pi will cancel with that pi. One of those r's will cancel with one of those r's. So we've just got r times 50 minus pi r squared. Or we can expand it out and it is 50r minus pi r cubed. Okay, so we've got a cubic volume function, a negative cubic. Looking at the factorised version, clearly has an x-intercept at r. The other factor being quadratic means there'll be 2 other x-intercepts. So it's going to look something like this. Sorry, it has an x-intercept at 0. I think I said r before. So it's going to look something like this. Now, obviously, we're talking about volume and we're talking about radius, and so therefore we're not going to be interested in these parts. So we want to focus on maximising volume, so finding the turning point, okay, finding the value of R that gives maximum volume, or we actually just want the greatest volume. So this is the value here that we're trying to find. Okay, so let's focus on finding the stationary points. So we're going to need derivative, dv dr. Now again, you're going to have your I'm going to have my CAS here in all of these application problems. Now that we're in sort of application, extended answer kind of question area, these sorts of things would occur in Tech Active assessment. So let's also think about how we can use our CAS to help us here. But again, you don't want to use it just because it's there. You know, this is a very easy derivative. 50r, derivative of that is 50, minus, you know, pi r cubed is 3 pi r squared. So really, you know, thinking about, sorry, that R looks a bit like a V, thinking about what you can do relatively easily by hand. I might define the function while we're here just so we can sort of compare that as we go. So menu 1.1 to define a function. V of R is equal to, now our function is 50R minus pi r cubed. Okay, to find our function, we can then calculate the derivative, shift minus, so shift minus being the shortcut for derivative, derivative of that. Sometimes when you're going to solve extended problems, it can be helpful to actually define that derivative. So you might actually, and you don't even need to actually really work out what the derivative is here, so you might define another function. I think a good habit to avoid having lots of different function names and not remembering what's what is if you want to define the derivative of v, I'm just going to call that dv of r, the derivative of v, okay? I think that's a helpful sort of habit to get into if you want to also define the derivatives. And again, I don't even need to know what the function is. I can just define the dv of r as derivative of r. And that just makes working with these two functions a bit easier when you're dealing with extended problems. So just some sort of tips as we go through. Okay, so we're trying to find stationary points, so we're going to want to solve this equal to 0. Now again, I can do this with my CAS. I can solve. I've now defined my nice derivative function, so I can solve dv of r equal to 0 for r. And when my CAS does it, it actually gives me a really ugly expression. It's not incorrect, and if you've got your CAS, there'd be nothing wrong with saying that. But again, this is a very easy equation to solve by hand. Adding 3 pi r squared to the right-hand side gives me 3 pi r squared equals 50. R squared equals 50 on 3 pi. And so r is plus or minus square root of 50 on 3 pi, which is a much easier expression to deal with than 5 root 6 over 3 root pi, personally, I think. Now, we've got r could be a positive or negative value, but obviously we've got context here. We know that it's radius, and so r has to be positive. and so r must be positive 50 over 3 pi. I would say in any problem, not just these kinds of problems, you shouldn't be ever rejecting a solution without giving a reason for doing so. So in the solution of that equation, we get r equals plus or minus a value. Even if I used my CAS to solve it, I'd still write down that I get plus minus 5 root 6 over 3 root pi. But because r has to be positive, r must be positive 50 over 3 pi. Or if you're using the CAS version, that as well. Okay, so we've found a value for r. So this function, however, had two stationary points. So we need to be clear about the fact that that is indeed a maximum stationary point because we're trying to maximise volume. So that is the r coordinate of one of the stationary points. We now need to show that that's a maximum. So we've talked about this previously. We want to make use of a sign diagram here. So I might just get my CAS, and this is where you want to use the two in conjunction. I'm just going to press Control Enter here to get an approximate decimal answer for that. So r is approximately 2.30. Okay, so 2.30, what's our units here? Centimetres, I think? Yeah, so surface area is centimetres squared, so the radius must be in centimetres. Okay, so now I want to justify that I've got a maximum value here. Okay, so we're going to set up our sign diagram, which remember we think we look at two values, one value either side of this value of r. Okay, so we're going to have r equals, we're going to work out what dv dr is, and then we're going to draw an inference about the shape of our graph. Okay, so we are looking at r equals square root of 50 on 3 pi, which is about 2.3. Okay, so therefore I'm going to look at when r equals 2 and when r equals 3. So we know the derivative is 0 at this point. That's all we know. We know it's a stationary point. We need to justify that it's actually a maximum stationary point. And so I'm going to be I want to substitute 2 into my derivative and 3 into my derivative. And this is where having defined my dv of r is helpful, because if you want to substitute values into the derivative without having defined the function, let me just show you how you would do it. So you need to get your derivative. So it's r in this instance, ddr of v of r, and then if you want to sub into the derivative, you need the given that r equals 2, r equals 2, and Control Enter to get that as a decimal. Whereas because I've defined my function as my derivative as dv of r, if I just type, dv of 2, it's going to sub 2 into the derivative straight away. Again, Control Enter. So, I've created that nice sort of shortcut that makes it a bit easier to work with my CAS. So I also want the derivative at 3, Control Enter for a decimal. Okay, so this is about 12.3, this is negative 34.8, okay? Whatever rounding you use there is fine, you're just giving a numerical value that justifies whether you have positive or negative gradient, but you do need to calculate a value specific to this function. You can't just say, oh, derivative gradient's positive when r is 2 and negative when r is 3, and so therefore it's a max. That's just a generic statement. There's no evidence that you've actually verified that that is true for this particular function. Okay, so your shape of your graph, we have positive gradient, zero gradient, and negative gradient, and so therefore we have a local maximum at r equals that value. Now that's the only stationary point within the domain of this function, the implied domain of this function. We thought a little bit about the graph up here. It's the only stationary point in that domain, and so therefore it must be the absolute maximum, given it's the only one over the domain of this function. Okay, so therefore we know that, not therefore, so this sign diagram tells us that r equals square root of 50 over 3 pi gives maximum volume. Okay, I want you to be really careful about the phrase or the sentence that you might write at this point. Sometimes people write r equals whatever is max. It's not the maximum, it is the value of r that maximizes the volume. Okay, so it's important that you're clear about that. Max volume happens when r equals this gives max volume, but be clear about r equals this is not the maximum. Okay, now, so we have done We've done step 2. We've found the absolute maximum or minimum point and justified that it is indeed a maximum. And now we need to answer the question, which is to find the greatest volume that the cylinder can have correct to 2 decimal places. So we're actually not interested in the R value, we want the volume. And so that means we need, so our maximum volume is going to be essentially V of that value. So again, over in my CAS, I can type in, V of square root of 50 on 3 pi. Okay, or the other version from the CAS. Control Enter, and so our maximum volume is 76. Now, sorry, what was the accuracy again? Correct to 2 decimal places. 76.78 cubic centimetres. If the question didn't ask us for a rounded answer, we just wouldn't hit Control Enter here. There's our exact maximum volume. Remember, only give rounded values where the question specifies it. Now, I made a manual adjustment to the question as it was originally asked. I think in terms of it being a meaningful answer in the given context, 500 root 6 over 9 root pi is a bit useless when I'm thinking about the volume of the canister. So yeah, I adjusted the question, but be clear about the fact that without that adjustment, so if I hadn't written here correct to 2 decimal places, you would be expected to give that answer as you can see it there on the CAS. Okay, so there's our first example complete. Alright, let's have a look at the second example. So here we have a gutter with length k inches, gutter with length k inches is made so that its cross-section is an isosceles trapezoid with dimensions as indicated in the diagram. Determine the value of theta so that the volume of the gutter is a maximum. Okay, what are we trying to maximise or minimise? Volume. Now, interestingly, we want to determine the value of theta that will give maximum volume. So it would be easiest if we can set up our equation for volume in terms of theta. Okay, so theta is obviously an angle we can see in this diagram. Let's just be clear about what's happening here. So this is the cross-section of the gutter. So what you've got to imagine is the gutter is extending out here. In fact, it tells us it has length k inches. Okay, so the gutter, runs lengthways. We are just looking at the cross-section of that gutter here. The cross-section is an isosceles trapezoid. Okay, so trapezoid has 2 parallel sides. That's really it. When it's an isosceles trapezoid, however, these 2 side lengths are equal in length, which means obviously this angle here is the same as this angle over here. This length is the same as this length, etc., etc. Okay, so it's nice symmetry about the isosceles trapezoid. Okay, so we want to maximise the volume, okay, and therefore, given that the gutter has a fixed length of k inches, whatever k might be, we're going to be maximising the volume if we maximise the area of the cross section. Okay, so max volume occurs when we have max area of cross section, given that the length is a fixed length k that's not at all connected to the area of the cross-section. So we're actually looking at maximising an area here in order to maximise the volume. Okay, so we want to focus on coming up with an expression for the area of this isosceles trapezoid. So first of all, to think about the area as being split into 2 congruent triangles and a rectangle. Okay, so the area here is going to be the rectangle, which is clearly 10 by h, plus 2 of the triangles, which are L and H. And obviously we've got theta in there, which we'll talk about in a minute. Okay, so the area therefore is going to be 10h plus 2 times half times base times height. So that is 10h plus 2 times half cancel out, HL. Okay, so therefore we want area just in terms of one variable, and we could express it in terms of h or L by connecting h and L. We could do that using the right angled triangle and Pythagoras' theorem. But given that I want to find the value of theta that gives maximum volume, I actually want to try and express area in terms of theta. So let's think about how we might express h in terms of theta and L in terms of theta. So again, let's focus on this right-angled triangle. So we know that's 10, we know that's theta, this is L and this is h. Okay, so focusing on just connecting h and theta initially, okay, we could use some trigonometry in this right-angled triangle. So h, if we're looking at theta, h is the opposite side, and so sine of theta is opposite of our hypotenuse, which is h over 10. And so h is equal to 10 times sine of theta. We can use the same logic for L, except L is the adjacent side, so we need cos. We know that cos of theta is L over 10, which means that L is 10 times cos of theta. So therefore we can write our equation for area in terms of theta in this way. So we've got 10 times h, and h is 10 sine theta. And then we also have h times L, so that is 10 times sine of theta multiplied by 10 times cos of theta. Okay, so we have 100 sine theta plus 100 sine theta cos theta. Okay, so we can focus on finding our derivative. I might start off by defining my function, so I can use my CAS to help me along the way. So menu, we're going to have a of, I'll call it t for theta. A of t equals 100 times sine of t, just also checking that you're in radian mode when differentiating trig functions, plus 100 times sine of t times cos of t. Okay, so we've defined our function. So we could use our CAS to do the derivative. Sorry, didn't mean to caps, although your CAS doesn't make a distinction between lower and uppercase letters. Derivative of a of t. Okay, so we can get that there. Or you might have done it by hand, in which case you would get a slightly different expression. And that's because actually this area function simplifies using a trig identity that we don't need to know in this course, but it does mean that when your CAS does it, you get something slightly different. So if you'd done this by hand, dA dt, 100 times sine theta, derivative of sine theta is cos theta, so that would be 100 times cos theta, and then you would need product rule, so we would then have 100 sine theta, we'll differentiate the first part, so derivative of sine theta is cos theta. So again, we're going to have 100 times cos theta, so 100 cos squared theta, plus, if I leave the sine theta as it is and differentiate the cos theta, derivative of cos is negative sine, so actually it'll be minus 100 sine squared theta. So if you've done it by hand using product rule and your derivatives of trig functions, that's what you would have got. However, when you use your CAS, it gives you, let me just have a quick look, it's just written again, understanding how to read the cos of t all squared, we would normally write as cos squared theta, so it's 200 times cos squared theta plus 100 times cos theta equals minus 100. Now you do not need to know how to get from here from the first line to the second line, okay? They are correct and equal and valid both as answers, so just if you use your CAS you'll get this version, if you do your derivative by hand you'll get this version. In this particular instance you do not need to know how to go from one of those versions to the other. Okay, so either way we're looking at solving our derivative equal to 0. Okay, so I can get my CAS to do that for me. I might, back over here my CAS, I might just make a quick definition of my derivative function. So derivative of a in terms of t is equal to, literally, derivative of t with respect to t of a of t. And so now when I solve, I'm going to solve, now again you can scroll up and get any of these, or you can just type your dA of t. So again, getting used to working with your CAS, getting used to working efficiently, because you're going to be using it extensively through these application problems. Now obviously we're solving a trig equation here, and so without a domain restriction we get infinitely many solutions, which is perfectly correct and valid. So we want to think about our context here. So theta is an angle, okay, so we know, and it's an angle in a right angled triangle. So we know it actually has to be, it can't be any bigger than 90. So theta, or in my case it's t, is going to be somewhere between 0 and 90. Sorry, we are in radians, so pi on 2, between 0 and pi on 2. Okay, and when we do that, we get just one solution. So theta equals, now be careful, I was really tempted right then to just write t equals pi on 3. Be really careful about this. This is a common error you'll make. You must make sure that you use variables consistent with the question. So even if you're using a different letter in your CAS, be really careful about making sure that what you write down on the paper corresponds to what's actually happening on the page. So theta equals pi on 3. So we actually find within that domain there's only one point of 0 gradient, okay? So one turning point. So now obviously we need to justify that it is indeed a maximum turning point within that domain, and so we're going to use our sign diagram to do that. So theta equals, now we might think of an angle either side of here. Obviously it's going to need to be, you could go with pi on 6 and 2 pi on 3, or whatever it might be. You could go with 0 and pi on 2. They're potentially a little controversial because they are at the ends of the domain, but they will work, so there's no problem with that. So any two values either side of your stationary point. As I said, if you're a bit uncomfortable with the 0 and pi on 2, because technically you might argue actually the domain of this doesn't include 0 and pi on 2, okay, then we can go with pi on 6, which is half of pi on 3, and we can go with 2 pi on 3, which is double that. Okay, so whatever you're comfortable with, that's fine. Alright, so let's set up our sign diagram. Okay, so we want DAD. Actually, I just noticed after having said be careful about using variables consistent, I wrote DADT up here, so that derivative should be DAD theta. So we are calculating DAD theta, so the gradient at each point. So at pi on 3, the gradient is 0. At pi on 6, again, now I can make use of my defined function, so dA of pi on 6. Okay, so that's 50 root 3 plus 50, which is clearly a positive number. If you want to get that as a decimal, you can, but you should be able to tell that that's positive without needing a decimal value. And then derivative at 2 pi on 3, for example. Doesn't need to be these two values, just a number either side of pi on 3. Oh, I've just realised, sorry, 2 pi on 3 is bigger than pi on 2. My apologies. Let's just go with pi on 2 here then. That's going to be easier. So, obviously you could probably do something like, what could we do there instead? Yeah, you'd sort of have to get into twelfths. It's not really worth it. They're not going to be nice exact values. So probably easier just to stick with pi on 2. Sorry, that was my mistake. 2 pi on 3 being bigger than pi on 2 is out of the domain. So at pi on 2 is negative 100. Fortunately the same as at 2 pi on 3, but just be careful about that. It's not sort of valid to think about the gradient out there. We're not actually interested in it outside of that domain. Okay, so that means that the shape of our graph goes from having positive gradient, 0 gradient, to negative gradient. And so this tells us that theta equals pi on 3 gives maximum area. Alright, so then let's go back to what the question's actually asking us for again. Determine the value of theta so that the volume of the gutter is a maximum. So we've actually answered the question. So theta equals pi on 3 gives maximum area, which will ensure maximum volume. Now again, I know that it's an absolute, value. I know that it's an absolute maximum value because it's the only stationary point within the domain, and it is a maximum, and so therefore the graph doesn't turn around at any other point within the domain, so it can't possibly get higher than that. Okay, let's have a look at another example. Consider the parabola with equation y equals x squared and the point P with coordinates 3, 0. Show that the distance from P to any point on the parabola is given by that, and find the coordinates of the point on the parabola that is closest to P. Okay, let's have a look at setting up what we've got here. So part A is to show that. So let's set up the problem. So we've got the basic parabola, y equals x squared. Okay. And then we have got the point 3, 0, which let's assume, let's say that's the point 1, 1, so there's 1, 2, 3. It's sort of going to be somewhere over here. So it's certainly not on the curve. Okay, so this is point P. All right, let's pick a random point on our curve with an x coordinate of x, which means that the y coordinate will be x squared. Okay, so what we're looking to do in this problem ultimately is find the coordinates of the point on the parabola that is closest to P. Is we're trying to minimise the distance between a point on the parabola and P. So that's why part A is asking us to come up with an expression for the distance. Okay, so we are trying to find that distance there. So if we know our distance between 2 points, if you don't, distance between 2 points is just Pythagoras. Okay, Pythagoras' theorem tells us that this distance here would be 3 minus x, and this distance here would be x squared. And so, therefore, distance squared is x squared squared plus 3 minus x squared. Okay, you'll get to the same place using your distance formula. All it is Pythagoras' theorem. Let's tidy this up and show that it gives what's required in part A. So again, remembering that, show that question, you do not use the answer. Part A is essentially asking you, find an expression for the distance from P to any point on the parabola in terms of x. Hint, the answer should be this. Okay, so we haven't used that answer at all. We're working towards hoping that this gives the same thing as that answer. So x squared squared is x to the power of 4. Expanding out the perfect square here is 9 minus 6x plus x squared. Okay, so if we order that, it is indeed, and if we take the square root, let's do that at the same time, x to the power of 4 plus x squared minus 6x plus 9. So we have shown that the distance between the point P and any generic point on the parabola is given by this. So then part B is to find the coordinates of the point on the parabola that is closest to P. So closest to P means we're trying to minimise D. Okay, so, back before CAS, these were fairly common questions, and one of the things that you're encouraged to think about is if you're minimising the square root of something, the square root of something will be minimised when the something is minimised. So you can just focus on minimising this, and then if you've got the smallest possible value of that, then the square root of that will be the smallest possible value. But with the advent of CAS and things, you really it doesn't make any difference in terms of what you're going to do. So I wouldn't personally bother. I would just define my distance function and therefore find the derivative of that. Okay, so again, let's do a definition. So I'm going to define d of x, and it is going to be equal to the square root of x to the power of 4 plus x squared minus 6x plus 9. Okay, so we're going to need our derivative. Now we tend to avoid d as a function definition for this exact reason, dx, it's a bit ugly. So derivative with respect to x of d of x gives me this, 2x cubed plus x minus 3 over the square root of x to the 4 plus x squared minus 6x plus 9. And we want that to equal 0. So we can solve that equals 0 for x, which gives us x equals 1. So again, this function has only one stationary point, so therefore once we justify that that's a local max or min, it has to be an absolute max or min because the curve doesn't, the function doesn't curve again at any other point. Again, thinking about that idea that actually what you could have just done is focused on maximising or minimising this, the derivative of that would be 4x cubed plus 2x minus 6, which is essentially 2 times x cubed plus x minus 3. And so you'd be solving your derivative equal to 0, which is solving that equal to 0. Sorry, I lost there should be a 2x cubed in there, which is essentially that equal to 0, which is actually what we end up doing over here. Because if you're looking at when does a fraction equal 0, well, the only way a fraction is going to equal 0 is if the numerator equals 0. And so essentially all that we've done, in fact I'm doing it over here on my CAS, is we've solved the equation 2x cubed plus x minus 3 equals 0 for x, and indeed it gives us x equals 1. Okay, so again, you've got your CAS, you don't need to recognise those things, but it's worth sort of being able to think about that. The same idea in the previous example where we were trying to maximise volume, but we can do that by maximising area. This is the same kind of idea. If we're trying to maximise the square root of something, we can do that just by maximising the square root, or just by maximising the thing under the square root. Okay. Now, sorry, we're actually trying to minimise here, but same logic applies. Okay, so we found that there's one stationary point. We now want to justify that this is a minimum stationary point. Okay, so again, let's set up our sign diagram. We first want to have our x values, then we want to think about the derivative with respect to x, and we want to interpret what that means for the slope or the shape of our graph. Okay, so we know when x equals 1, we have 0, the derivative is 0. So we know it's a stationary point. So we could just look at 0 and 2, either side. Okay, so again, subbing into your derivative. Now, it might have been helpful if I set up my derivative equation, but I can still just go up here and at least take this bit and put given that. So get used to scrolling up, making use of things you've previously entered, editing, etc. So if we let x equal 0 in that derivative, we get -1. And again, very easy to make x equal 2. Just scroll up here, copy that down, change the 0 to a 2. So it's really important that you start using your CAS and getting used to it. And that is 15 root 17 on 17, which is clearly a positive number. So we've got -0, positive. Okay, so this tells us that minimum D occurs when x equals 1. So again, be clear, x equals 1 is not a minimum. The minimum value of D occurs when x is equal to 1. Okay, it's the x coordinate of the minimum turning point. Alright, so let's go back and be clear about what we need to answer here. So find the coordinates of the point on the parabola that is closest to P. So we know that the point on the parabola closest to P has an x coordinate of 1. Okay, and so this means that the y coordinate will be 1 squared, so also 1. And so therefore the point 1, 1 is the point on y equals x squared that is closest to the point P, which has coordinates of 3, 0. Okay, that's the third example. Let's have a look at the fourth example. Again, I've added a statement here that we're going to give our answer in kilometres, correct to 2 decimal places. Otherwise, you know, the exact answer becomes a bit meaningless in the context. Okay, so let's have a look at this situation. A camper is situated on an island shore at a point A, which is 17 kilometres from point B, which is the nearest point on the straight shore of the mainland. He wishes to reach town C, 45 kilometres along the shore from B, in the least possible time. If he can row his boat at 4 kilometres per hour and walk at 7 kilometres per hour, how far along the shore from B towards C should he land? Give your answer in kilometres correct to 2 decimal places. Okay, what are we trying to minimise or maximise? He wishes to reach town C in the least possible time. Least possible time, we are trying to minimise time. Okay, so we're then trying to come up with an equation for time. Now we've got information about distances and speeds here, so we're going to want to be able to think about the connection between distance, speed and time. So we know that speed is distance over time, okay? And so we can form our triangle that tells us that time therefore is distance over speed. I just marked some Year 10 tests this morning where students had real trouble getting that triangle correct. There's no magic there. It's very easy when you think about units. Speeds are given in kilometres per hour or metres per second. Distance divided by time. Okay, speed is distance divided by time. Start with that, and then you can rearrange for the quantity that you actually want. Okay, so we're going to want to think about that. Let's think about what's actually happening in terms of our diagram then. So we've got an island. Okay, I'm going to put my island out here, and I've also got the mainland, which is a straight shore. Okay, so Canberra is situated on an island at point A, which is 17 kilometres from B, the nearest point on the straight shore of the mainland. Okay, so let's have point A here. Point B, if it's the nearest point, it's the closest point will mean that that line meets the shore at a right angle. Okay. Any other point, if I look at this point over here, I've created a right angle triangle. This is the hypotenuse, and so therefore it is longer than the perpendicular length. Okay, so it's always going to be the perpendicular distance will be the shortest distance. Okay, so we know that's point B on the island, 17 kilometres from A. So this is 17 kilometres, this distance. He wishes to reach town C, which is 45 kilometres along the shore from B. Okay, so let's put C over here, and that is a distance of 45 kilometres from B to C. So we want to get, ultimately, from A to C. Now, obviously, the shortest distance from A to C is to just go straight there. But the challenge here is that he rows his boat slower than he walks. Okay, so if he rowed quicker than he walks, then obviously taking the distance that involves only rowing would be the quickest way to go. However, because his rowing speed is slower than his walking speed, there's going to be a point where he should row to here, for example, and then walk. That will actually ultimately minimise the time. So let's create an extra point here, which is actually what we're trying to find. We want to know how far along the shore from B towards C should he land. So this is the distance we're trying to find. Let's call that X. That's what we're trying to work out. Where should he land so that he minimises his time? So that means that this distance here is now 45 minus X. Okay, so the journey he's going to take is he's going to start at A, he's going to row to X, and then he's going to walk from X to C. Okay, so we want to think about those distances and speeds so we can think about time. So we know the walking speed is 7 kilometres per hour. We know the rowing speed is 4 kilometres per hour. So we need to think about the rowing distance. Okay, so the rowing distance, so let's think about that. Let's maybe call that, and I'll introduce another letter here, let's call that Y. We need to find that distance there. So thinking about that right angled triangle, we can use Pythagoras, so we can say that x squared plus 17 squared equals y squared. So we know y squared equals x squared plus 17 squared. Now 17 squared is 289, so y is the square root, it's only the positive square root because it's a distance, x squared plus 289. So that's this distance here. So that is that distance there. Okay, so let's think about the time. So the total time, I'm going to call that T, is the rowing time plus the walking time. Okay, so that means we know that time is distance divided by speed, so we need the rowing distance divided by the rowing speed. The rowing distance is square root of x squared plus 289 over the rowing speed, which is 4, plus the walking distance, which is 45 minus x, over the walking speed, which is 7. So there is our expression for the time it is going to take to travel this journey in terms of x, which is this value here that we're trying to find. Okay, so now we need to focus on minimizing time. So we want to differentiate this, dt dx. Again, I can get my CAS involved here. Not that that's a derivative that you shouldn't be able to do by hand, but thinking strategically about when it's going to be more efficient. So I'm going to define my function first. It's going to be t of x, and it is the square root of x squared, x squared plus 289 over 4 plus control divide 45 minus x over 7. Now again, if you are going to do this derivative by hand, thinking about the fact that these don't require the quotient rule, you're dividing by a number. This is just a quarter of the square root of whatever. So a quarter of something to the power of a half, differentiate that. This is just 45 on 7 minus x on 7. So thinking about, not unnecessarily using quotient rules where they're not needed. So I've defined my function, my derivative, shift minus, with respect to x, of t of x is this. So it is x over 4 times the square root of x squared plus 289, and then just minus 1/7. So the 45 on 7 is just a number that goes away. You've got negative x on 7, that's negative 1/7 x. That's where that negative 1/7 is coming from. And the first part is coming from your chain rule with that square root. So you should be able to get the same answer by hand. We're looking at when the derivative equals 0 because we're interested in stationary points because we're trying to find the minimum point. So we are going to solve this function equal to 0 for x. And when we do that, we get that x is equal to 68 root 33 over 33. If you want an approximate decimal value for that, that is 11.84 kilometres, which seems logical, doesn't seem impractical in our situation. Okay, so then we need to now justify that this value actually minimises time rather than maximising time. If it maximises, if that's a maximum turning point, that means that the absolute minimum must be happening at an endpoint. Then you've got to think about, the endpoints of this particular function. Alright, so let's see what's happening there. So x is going to be equal to, now 68 root 33 on 33 is about 11.84. So let's just look at 11 and 12 either side of there. Okay, so setting up my sign diagram, dt dx, and what that means for the shape. Okay, so we know that the derivative at 68 root 33 on 33 is 0. That's our stationary point. We want to know what is the value of the derivative at 11 and what is the value of the derivative at 12. So again, you could have defined your derivative function, or I can just scroll up here and get this, and I want to find out the derivative given that x is equal to 11. Let's get a decimal value there. That's negative 0.007, and the derivative when x is equal to 12 is 0.0013. Okay, so we've got negative gradient, small, fine, but it's still negative, 0 gradient, positive gradient, and so we certainly do have a minimum point when x is equal to 11.84. Let's go back to work out what the question's asking us for. How far along the shore from B towards C should he land? So we're not interested in what is the minimum time he can do the journey in. We are interested in the value of x that gives minimum time, which we actually already have. So therefore, so this sign diagram implies that x equals 68 root 33 on 33 gives minimum time. So therefore, he should land. So again, answer the question. The question says, how far along the shore from B towards C should he land? he should land 11.84 kilometres from B towards C in order to minimise time. He should land, just check that rounding, yep, 11.84. He should land 11.84 kilometres along the shore from B in order to minimise time. Just checking that rounding, sorry, whether it said 2 decimal places, yes. In kilometres to 2 decimal places, so 11.84 kilometres. If it said, let me just go back up to that number, so here's the answer up here highlighted in blue. If it said to give your answer to the nearest metre doesn't mean that you need to give your answer in metres, you just need to give enough accuracy so that it's rounded to the nearest metre. So to the nearest metre it would be 11.837 kilometres, which is 11 kilometres and 837 metres. So it doesn't mean you need to give, it doesn't mean you need to convert to metres, it just means you need to give enough decimal places that it is accurate to the nearest metre. Okay, let's have a look at our final example here. A company produces items at a cost price of $2 per item. Market research indicates that the likely number of items sold per month will be 800 over p squared. Okay, so we've got this sort of inverse relationship here where obviously the larger the cost, the less items that will be sold. Okay, p dollars is the selling price of each item. Sorry, so the larger the p is the selling price. So the larger the selling price, the less items that will be sold. But obviously there'll be this nice balancing point where we get the selling price right, and okay, we might sell a few less items, but ultimately we're still making more profit. If we make the selling price too high, we'll sell too few items to make good profit. If we leave the selling price too low, we might sell a lot of items, but we're not making enough profit. So we're looking for that nice sweet spot where we can, how do we set the selling price in order to maximise the profit? Finding the value of P for which the company would expect to maximise profit and the corresponding number of items sold. So this will be an important one where that last step, answer the question, is important because it's asking us for a couple of things here. So we want to make sure we give everything that's needed. Okay, so we're maximising profit. So we need to come up with an expression for profit. Okay, so we can think about this in a couple of different ways. So if we think about the profit per item, it's going to be the selling price minus the cost. Okay, so we sell the item for p dollars and it costs us $2 to make it. So therefore we make p minus $2 per item. Okay, so then if we think about the profit per month, it tells us in 1 month we will sell this many items and we're going to sell each of those. So we're going to sell 800 over p squared items and each of those is sold for p minus $2. So therefore our profit per month, let's call it something, I'm not going to call it capital P because then I'll have P in terms of P and it's a bit confusing. I might just use M maybe. Let's make profit per month is going to be 800, you can choose any letter, it doesn't matter. Okay, so that's our function for profit per month. Now you might choose to expand that out, obviously that's going to be 800p on p squared, so it'll be 800 on p minus 1600 on p squared. Again, a nice easy derivative to do by hand, so no reason not to do that. I'm going to set things up in here so I can do my sign diagram and things nice and easily, given that I have it, but the numbers and the calculations here would be perfectly feasible to do this tech-free. So defining my function, it is m in terms of p. I mean, you could always define everything as f of x, but defining in your CAS using the same variables as the question will help you to avoid that transcription error that happens where you all of a sudden change p to x randomly in your calculations and therefore what's on the paper is no longer correct. So you can help to avoid that by actually using the same letters in your CAS as you're using on paper. So 800 on p minus 1600 on p squared. So again, you could also define the unexpanded version, there's nothing wrong with that. Okay, so we've got our function defined, derivative, shift minus, derivative with respect to p this time. I'm sorry. As I said, it doesn't matter if it's a capital, but the CAS doesn't differentiate between them. So we're calculating the derivative with respect to p of m of p. Oops, m of p. So dm dp is 3,200 on p cubed minus 800 on p squared. You would have got that exact same expression by hand as well. We want that to be equal to 0. We are trying to maximise profit, so we're looking for stationary points of this profit function. So solving menu 3.1, solving this equation equal to 0, equal to 0 for p, and we get p equals 4. When you're using your CAS, it's still important that you write down an equation. Okay, so you can't just straight away write down p equals 4. So dm dp equals 0. Technically dm dp equals 0 would be enough without writing this, but I'm strongly going to encourage you to get in the habit of actually writing down the derivative. I have seen the year that I marked exams, there be some argument about students that didn't write down the derivative. Now I would argue you've got your CAS, dm dp equal to 0 is the equation, or m dash of p equal to 0 is the equation, that should be sufficient. But I have seen some inconsistency around that, so I would encourage you to always write down the derivative equal to 0, and then you can just give your answer. Okay, so we've got one stationary point again, so it must be an absolute max or min, as long as we can justify that it's a max or a min. Okay, so p equals either side of 4, let's just go with 3 and 5. We want to calculate dm dp. And we want to then interpret what that means for the shape. Okay, so we know when p equals 4, dm dp equals 0. We want to know what is dm dp when p equals 3 and 5. Alright, so again, I haven't defined my derivative function. Just going to do it this way. So, and as I said, mostly easy by scrolling up and copying down that derivative expression. I'm going to need to enter in the given that p equals 3. So we get 800 on 27, which is clearly a positive value. And then I'm just going to edit that previous calculation when p equals 5, and we get negative 32 on 5, which is clearly a negative value. So positive, 0 gradient, and then negative gradient. And so this sign diagram tells us that p equals 4 gives minimum, sorry, not minimum, just proved it's maximum, gives maximum profit. So again, not p equals 4 equals is a max, it is p equals 4 gives maximum profit. Okay, let's be clear about what the question actually asks for. It asks us to find the value of p for which the company would expect to maximise its profit. We've just done that. And the corresponding number of items sold. Okay, so we know this is the number of items sold, 800 on p squared. So we are obviously going to need to work out p equals 4 gives maximum profit, and that means that 800 on p squared is 800 on 4 squared, which is 800 divided by 16, 50. Okay, so therefore, max profit occurs when the selling price is $4. This will result in selling 50 items per month. Okay, again, the numbers in this problem are nice, and so actually this could be achieved completely tech-free. So it's not to say you won't ever be asked to do a max and min problem in a tech-free assessment. You absolutely could, but where we're at the moment, and in preparation for the SAC, which will be done with the use of your CAS, I want you to start to get used to practicing using your CAS and, you know, learning those routines. There really is a lot of efficiency that's gained from practicing with your CAS. It's really important that you've got your CAS with you, it's charged, and you're able to use it to help you to solve these problems. Exercise 10F is the work for today. Application, max min applications. There are lots and lots and lots more application of max-min application problems in the chapter review. There is 49 extended response questions in the chapter review. Some of those are rates of change. The vast majority of them are maximum minimum problems, just like these. So lots and lots of practice to be had.